Hi, and welcome to a third example on finding the length of a curve. By this time, you should be pretty good at this, so this is a little bit more challenging. The first thing we need to do is look at our function. If we look at our function, we notice that it's a function of y in terms of x. So when we use our equation, and I'll put it up here, we need to use the length of the curve equation that is defined from a to b. And we're going to take the square root of 1 plus dy dx quantity squared with respect to x. Okay? Now, the first thing we need to kind of think about with this is this absolute value and what this looks like. Whenever you have an absolute value and you need to do derivatives, you kind of need to split it into a piecewise. Let's go ahead and look at the graph of this as well, because I like to look at the graphs of absolute value and piecewise functions. Alright, so when we look at the graph of this, we notice we've got the parabola shape, but we've got it twice. So let's go back to our function and see if we can figure out how to split it up. In order to split this up, we need to think about what an absolute value does to a function. The absolute value does nothing if what we put into x is 0 or greater. So we could rewrite this as x squared minus 4x minus x if x is greater than or equal to 0. We don't really need the absolute value sign at all if this is true. However, we do need the absolute value sign if x is less than 0, and what the absolute value sign does is it effectively takes the opposite of that negative number. So if we're looking at x values that are less than 0, what that absolute value sign is going to act like, it's going to act like a negative. So we're going to take minus a negative, so we could rewrite that piece x squared plus 4x minus x if x is less than 0. And we have split our absolute value function into two pieces. So let's go ahead and make sure that that's accurate. We're going to go back to our graph. And if you look at the graph, what I've done is I've put the two pieces, our piecewise, this is for the values of x that are greater than 0. If I graph that, you can see I get the right-hand side of the absolute value function. And then this graph was for the left-hand side, or the values of x that were less than 0. If I graph that, I get the other piece here. So you can see that these two pieces together make that absolute value function, and it all comes together in this kind of interesting shape. Now if you notice, we have a cusp at 0, so, well, it's not actually a cusp, it's more of a corner, but we don't have differentiability at 0. So when we do this length of a curve, we're going to have to split this into two integrals. Alright, so now that this makes a little more sense, let's go ahead and take the derivative of this y. So our dy dx is going to look like this. Okay, so when we take the derivative of a piecewise function, remember, just take the derivative of each piece. This simplifies into x squared minus 5x, so the derivative would be 2x minus 5. This simplifies to x squared plus 3x, so the derivative would be 2x plus 3. Now, we know this is true if x is greater than 0, and we know this is true if x is less than 0. Notice I got rid of this equality sign here because we don't have differentiability at 0. Going back to the graph, we have this corner at 0, therefore we don't have differentiability. The way you check for that analytically is you plug in 0 for the left-hand derivative and for the right-hand derivative, and you notice you get negative 5 and 3, so they don't agree. Now we can evaluate our length, and remember we have to split it up into two pieces. The first piece is going to go from negative 4 to 0. So the length is going to go from negative 4 to 0. We're going to use our derivative for values that are less than 0. Our next integral is going to go from 0 to 4. In here, we're going to use our derivative that works for values that are greater than 0. Alright, and now we're ready to put these in our calculator. When we put the left-hand side into our calculator, we get 9.7782 plus, and when we put the right-hand side, we get 9.7782, which is kind of interesting. There must be some symmetry going on here. And again, if we look back at our graph, we notice if we go from negative 4, which is right about here, to 0, that piece is going to mimic the piece from 0 to positive 4. And here I think I can show you that a little bit more clearly. I'm going to connect this point from negative 4 all the way to 4 here, and then I'm going to grab that piece of parabola I've just traced, and I'm going to move it, and you can see that those two pieces are exactly the same length. So that's why we have the symmetry, and the two values are the same. So let's go back up here. If we add these two guys together, we get our final answer of 9.7782, which rounded or truncated gets you 9.778. All right, I hope this example was a little more challenging, a little more interesting than the last two. Be careful anytime you have derivatives that do not exist in the interval that you're looking at, you have to split up the integrals. So be aware of that and keep your eyes peeled for it.